Everyone is focused on the wrong metal. For the past 2 years, Wall Street has been fixated on lithium, then cobalt, then copper. Investors looked at the rise of electric vehicles and made a simple conclusion. Cars need wiring, wiring is copper, so copper must be the big winner. On paper, that made sense, but it missed one critical detail. While analysts were publishing reports about copper shortages, the most innovative car company in the world was quietly changing the rules. Elon Musk and Tesla's engineering teams were not following the copper narrative. Instead, they were redesigning the entire electrical backbone of the automobile. They recognized that copper is heavy, costly, and inefficient at scale. So when Tesla launched the Cybertruck, they made a decision that stunned the automotive industry. They eliminated the traditional 12-volt battery system and replaced it with a 48-volt architecture. Most media outlets framed this as a simple cost reduction. They said Tesla wanted to use less copper, and that part was true. But what they failed to understand was the physics behind that change. Increasing voltage creates a serious new challenge. That challenge is arcing. At 48 volts, electricity behaves very differently. When a switch opens or closes, electrical current wants to jump across the gap. That jump creates a spark, similar to a tiny lightning strike. If that spark hits copper contacts, the metal degrades and melts. If it hits brass, the contacts weld together. Either way, the system fails. There is only one metal that can reliably handle this condition, only one element that can stop arcing without destroying the switch. That metal is silver. In this 4-part market update, we are revealing what we call the silver switch. We will show why Tesla's move to 48 volts is quietly driving massive new silver demand. We will explain why Ford, General Motors, and Toyota are now rushing to adopt the same standard. And we will calculate how many millions of ounces of silver this copper-reducing technology will pull from global inventories. Most people still believe electric vehicles are a copper story. Tesla just turned them into a silver story, and the market has not priced it in. To understand how significant this change is, we need to look backward. For nearly 70 years, every car on the road, from a 1955 Chevrolet to a 2020 Toyota, ran on a 12-volt electrical system. The reason was simple. It worked. 12 volts could start the engine, power the radio, operate windows, and run basic electronics. Just as important, 12 volts is safe. You can touch the terminals of a car battery and not get shocked because the voltage is too low to jump gaps. But modern vehicles are no longer simple machines. Today's cars include radar systems, LiDAR, heated seats, steer-by-wire controls, and large digital displays. A 12-volt system cannot handle this load efficiently. It's like trying to fill a swimming pool using a garden hose. To deliver enough power, manufacturers had to use thick, heavy copper wiring. In many modern vehicles, the wiring harness alone weighs more than 150 pounds. That weight reduces efficiency and driving range. It also raises production costs. Elon Musk looked at the numbers and realized that increasing voltage to 48 volts would reduce current by a factor of 4. Lower current allows thinner wires. Thinner wires require far less copper. Tesla reduced wiring weight by roughly 70%. That saved money, reduced mass, and improved performance. On the surface, it looked like a clear win, but physics always comes with trade-offs. Higher voltage increases heat and electrical arcing. This is the part most investors missed. At 48 volts, when a switch opens, electricity can jump across the air gap. That creates a plasma arc, with temperatures reaching thousands of degrees, even if only for a split second. Copper contacts degrade under this stress. Carbon buildup forms. Eventually, the contacts melt or fuse together. Imagine trying to turn off your headlights and the switch is permanently welded on. Or imagine a steer-by-wire relay failing due to contact damage. For a company focused on reliability and autonomous driving, this risk is unacceptable.
Elon Musk needed a material that could survive extreme heat, resist arcing, and remain conductive even after surface oxidation. That material is silver.
Tesla did not place silver bars inside vehicles. Instead, they used a specialized alloy called silver tin oxide. This material is now standard in high-voltage automotive relays. If you examine component specifications from manufacturers like TE Connectivity or Bosch, you will see the change clearly. When systems move from 12 volts to 48 volts, copper alloys are replaced with silver-based contacts. Every time a Cybertruck window is activated, silver contacts close the circuit. Every time the autonomous system applies the brakes, a silver relay engages. The entire electrical nervous system is protected with silver surfaces to prevent failure or fire. This is not a cost-cutting situation where silver usage is reduced. In fact, the opposite is true. At 48 volts, safety standards require thicker silver contact points. You cannot reduce silver content without risking failure. The laws of thermodynamics do not allow shortcuts. Tesla saved roughly 50 pounds of copper per vehicle, but in exchange, they added ounces of silver. They replaced an abundant base metal with a scarce precious one, and they did it across millions of vehicles. If Tesla were the only company doing this, the impact would be limited. Tesla produces around 2 million vehicles per year. The silver market could absorb that. But Tesla does more than manufacture cars. Tesla sets industry standards. Once Tesla proved that 48 volts reduces cost and weight, the rest of the industry reacted quickly. Ford, General Motors, Toyota, and Volkswagen all face intense pressure to improve efficiency and cut expenses. They examined the Cybertruck and reached the same conclusion: they must follow. In a strategic move, Tesla even shared 48-volt design documentation with other automakers. They want the industry to adopt the standard because it builds a shared supply chain for 48-volt components. Now, the scale changes dramatically. Instead of 2 million vehicles, we are looking at a global production rate of roughly 90 million vehicles per year. Over the next decade, the industry will transition from 12 volts to 48 volts. This is not optional. It is inevitable. Every one of those vehicles will require silver-heavy relays and connectors. This demand is separate from solar panels and separate from investment demand. It is a new structural layer of silver consumption added to an already tight market. High voltage creates arcing. Arcing requires silver. The question now is how much silver this actually means. In Part 2, we begin the calculations. We break down a modern 48-volt vehicle, count relays, connectors, and control systems, and estimate silver content per car. Then we multiply by global production. The results are surprising. They suggest that the automotive sector alone could consume 50 million to 100 million ounces of additional silver within the next 5 years. Global mining produces about 800 million ounces annually. There is no easy source for that extra metal unless prices rise dramatically. This brings us deeper into the investigation. If you are just joining, here's what we have established. Tesla eliminated the 12-volt system. Moving to 48 volts reduces copper use, but creates arcing risk. Silver is the only viable solution, but theory is not enough. We need real numbers. Wall Street models still assume automotive silver demand grows by just 2% annually. That assumption is outdated. The 48-volt shift is not incremental. It is a complete redesign of the global vehicle electrical system. In Part 2, we virtually dismantle the Cybertruck. We examine zone controllers, relays, redundant systems, and safety circuits. Then we scale the numbers. The Cybertruck is the first mass-produced vehicle with full steer-by-wire technology. There is no mechanical steering column. Turning the wheel sends a digital signal to motors on the axle. This design requires perfect electrical reliability. Even a millisecond failure could cause an accident. To prevent that, Tesla built redundancy everywhere. Backup circuits, backup relays, backup power pathways. Each redundant system increases component count. And because all of it operates at 48 volts, every critical contact uses silver. Tesla also replaced traditional fuse boxes with intelligent electronic fuses controlled by silicon and silver. These systems switch power constantly, generating heat. Silver minimizes resistance and heat buildup. Historically, internal combustion vehicles used about 15 to 20 grams of silver. Standard electric vehicles use roughly 30 to 40 grams. The inverter, battery management, and charging systems add more. With 48-volt architecture, estimates suggest an additional 20 grams of silver per vehicle just for switching and safety systems. That brings total silver content to 50 to 60 grams per car, approaching 2 ounces. That number sounds small until you apply scale. Global vehicle production is around 90 million units per year. If only 50% adopt 48 volts by 2028, that is 45 million vehicles. 45 million times 20 grams equals 900 million grams, or roughly 29 million ounces of new annual demand. That is conservative. Higher autonomy levels could push usage toward 3 ounces per vehicle, creating demand of 50 to 60 million ounces per year. For comparison, all primary silver mines in the United States produce about 30 million ounces annually. One design change has created demand larger than an entire national mining industry. Tesla reduced copper use by 25%, but replaced it with silver. Less metal by weight, higher quality metal by necessity. This is the broader technological trend. As systems become smaller and more powerful, materials must improve. The industry upgrade is locked in. The blueprints are finalized. Suppliers are retooling. The demand is real. Now we turn to supply. Silver production has not increased meaningfully in over a decade. The reason is simple. About 72% of silver is produced as a byproduct of mining other metals like zinc, lead, copper, and gold. If base metal prices fall, silver output falls too, regardless of silver prices. This creates inelastic supply. Even at $100 per ounce, silver output may not increase. Ore grades have also collapsed. In 2005, primary silver mines averaged 13 ounces per ton. Today, many operate at 4 to 5 ounces per ton. More rock must be processed for the same output, increasing costs and reducing profitability. Exploration budgets have been cut for years. New mines take 10 to 15 years to develop. Even a discovery today would not produce silver until 2040. Tesla needs silver now. Geopolitics add another layer. Mexico produces roughly 25% of global silver supply. Political changes there include higher taxes, permit restrictions, and resource nationalism. This threatens North American supply chains. Refining is another bottleneck. Much silver concentrate is refined in China. With China building its own EV industry, refined silver may not return to Western markets. This creates regional shortages and price premiums. The result is a violent repricing. The auto industry is price insensitive. If silver rises from $50 to $500 per ounce, the cost impact per car is under $1,000. Manufacturers will pay it. We saw this with rhodium in 2020. Prices exploded and automakers paid. Recycling will not solve this quickly. Vehicles last 15 to 20 years. Silver installed today will not return until 2040 or later. The conclusion is unavoidable. Structural deficit is forming. Demand is locked in. Supply cannot respond. For investors, this is opportunity. Focus on North American primary silver miners. Jurisdiction matters. Compliance matters. Strategic supply matters. Physical silver provides insurance. It benefits from both technological demand and monetary instability. The facts are clear. Tesla moved to 48 volts. Silver is required. The industry is following. Supply is constrained. Prices must adjust. The 48-volt revolution has begun. Make sure you are ready. Subscribe.